And now on to the next part of our discussion on vibratory motion. Let's look at a few examples. So we have sample problem number 1. A 0.68 kilogram block is attached to a horizontal spring. The block is pulled 11 centimeters and then released. The block is pulled 11 centimeters, resulting in the spring being stretched 11 centimeters. And as a result, the block will undergo spring motion. The spring has a spring constant of 65 Newton per meter. Ignoring friction, determine the following items: the frequency and period of the resulting motion, the amplitude of the oscillation. When we say oscillation, we're talking about vibration. Oscillations and vibrations, as far as our course is concerned, they are one and the same. The maximum speed of the oscillation, and lastly, the acceleration function. We know the mass of the block, 0.68 kilograms. Let that be mass M. The block is pulled 11 centimeters, resulting in the spring being stretched 11 centimeters. Let that be X. X is equal to 11 centimeters. Convert to meters. The spring has a constant of 65 Newton per meter. Let that be our spring constant K. We are looking for frequency of the vibratory motion, period of the vibratory motion, amplitude of the oscillation, the maximum speed of the oscillation, so Vmax, and the acceleration function A. One of the equations for vibratory motion, in particular for periodic motion, we have omega is equal to square root of k over m, an equation particularly applicable for spring motion. We know the spring constant k, we know the mass of the block m, thus we are able to calculate the angular frequency 9.776923.611 radians per second. Another equation for omega is equal to 2 pi over t, period. Isolating t is equal to 2 pi over omega. We have just calculated omega, thus we are able to determine the period of the vibratory motion, 0.642,654,6383 seconds. And the inverse of period is just frequency. So knowing the period, we also know the frequency of the vibratory motion. 1.556045,721 Hertz. So frequency is 1.556 Hertz and period is 0.643 seconds. Next, we look for the amplitude of the vibratory motion. To start the vibratory motion, the block is pulled back 11 centimeters. So let that be the initial position X initial. And then the block was released, which means the speed of the block is 0. Let that be the initial speed V initial. So for the initial case of the block, we have X initial and V initial. Using the energy equation for spring motion, the total mechanical energy at any location is equal to 1/2 Ka squared. So this is any location. Let's choose initial position or the initial location. So we have X initial and V initial. For the initial location, we have initial kinetic energy plus initial potential energy. is equal to 1/2 Ka squared. The initial speed is 0, therefore the initial kinetic energy is 0. Initial elastic potential energy is 1/2 Kx initial squared, and that's equal to 1/2 Ka squared. Comparing the two sides of the equation, we see that the amplitude A is just equal to x initial, 11 centimeters. So the amplitude is 11.000 centimeters or 0.110 meters. Knowing the angular frequency, 9.776923.611 radians per second, and knowing the amplitude, 0.110 meters, we are able to determine the maximum speed of the vibratory motion since Vmax is just equal to A omega. Knowing A, knowing omega, we are able to calculate Vmax. Vmax is equal to 1.075 meters per second or 107.546 centimeters per second squared. To get the acceleration function, we know the general equation for the acceleration function. A is equal to negative A omega squared cosine of omega t plus phi. We know omega. We have just determined omega when we look for the period and the frequency of the vibratory motion. So we know omega, and we have just determined the amplitude A. To be able to complete the equation, we need to determine the phase constant phi. So to determine the phase constant phi, we use the position function. X is equal to A cosine of omega t plus phi. We know the initial position x initial, and initial speed vi. So the initial case is known to us. So let's set the time to initial time. So let t is equal to 0. At t is equal to 0, x is just equal to x initial. T is equal to 0, omega t is 0. So we get x initial is equal to A cosine of phi, which means cosine phi is just equal to x initial over A. We know x initial, we know A, 0.11 meters divided by 0.11 meters will just give you 1. So cosine phi is equal to 1. Get the inverse cosine, you get phi is equal to 0. So our equation for the acceleration function is now complete. A omega squared is just 10.515 meters per second squared. So we have A is equal to negative A omega squared. So negative 10.515 meters per second squared cosine of omega t. Omega is 9.77 radians per second. So again, we have the acceleration function. A is equal to negative 10.515 meters per second squared cosine of 9.777 t. Note that the calculations that we have just done, for many problems, this sort of calculations is just the beginning of the analysis. So please bear that in mind. And now we have sample problem number 2. At t is equal to 0, the position of a particle in a linear oscillator is negative 8.50 centimeters. Likewise, at t is equal to 0, the particle's velocity is negative 0.920 meters per second. And its acceleration is positive 47 meters per second squared. Determine the phase constant and the amplitude of the oscillation or vibratory motion. We have the position x at t is equal to 0, negative 8.50 centimeters. Convert to meters. We have the velocity at t is equal to 0, negative 0.920 meters per second. Likewise, we have the acceleration value at t is equal to 0, positive 47 meters per second squared. Using this information, determine the phase constant phi and the amplitude A. So we have x, v, and A. We use the position function x, velocity function v, and acceleration function A. First, the position function x. X is equal to A cosine of omega t plus phi. If we set t is equal to 0, omega t will be equal to 0, and x will be equal to x at t is equal to 0, negative 0.085 meters. So we have negative 0.085 meters is equal to A cosine phi. We do the same thing for the acceleration function. Acceleration function is negative A omega squared cosine of omega t plus phi. We set t is equal to 0, which means A will just be equal to A at t is equal to 0, positive 47 meters per second, and omega t will be equal to 0 because t is equal to 0, giving us negative A omega squared cosine phi. Dividing x by A, we have negative 0.085 divided by 47 is equal to A cosine phi divided by negative A omega squared cosine phi. We can cancel out cosine phi. We can cancel out A, leaving us with omega as the only unknown. Omega is the only unknown in the equation, so isolating omega, we are able to calculate omega, the angular frequency of the vibratory motion. Omega is equal to 23.51470128 radians per second squared. So we got an answer, but that's not quite the answer that we are looking for. We are looking for phi and A. But we still have the velocity function. V is equal to negative A omega sine of omega t plus phi. We do the same thing that we did with A and x. We set t is equal to 0. Therefore, V is just equal to V at t is equal to 0. Negative 0.920 meters per second. Omega t is equal to 0 because t is equal to 0. So we have negative A omega sine phi. Dividing x by v, we get negative 0.085 divided by negative 0.920 is equal to A cosine phi divided by A omega sine phi. We can cancel out A. We know omega, we just calculated it. The only unknown is phi. So combining cosine phi and sine phi and isolating, we get tangent phi is equal to negative 0.460287769. And getting the inverse tangent will give you phi. Phi is equal to negative 0.431376 2271 radians. So by using this kind of analysis involving the position function, velocity function, and acceleration function, we are able to get a value for the phase constant phi. However, when we try to use the value of phi that we calculated, when we try to use that value to determine the amplitude of the vibratory motion, we get a negative answer. And I leave it up to you to try and see if you will also get a negative answer using the phi that we just calculated. So, there's nothing wrong with the analysis that we just did. So, how come this phi is not quite correct? It's not quite correct because amplitude should always be positive, and the amplitude that we will be able to calculate using that value of the phase constant is negative. So that means that value of the phase constant is not quite correct. The problem lies with the tangent function. The tangent function is a trigonometric function. And from trigonometry, we know that trigonometric functions, sine function, cosine function, tangent function, they will give you a same answer for certain values of the angle. So, tangent function will provide you the same answer for certain values of the angle. For instance, say we add the angle that we calculated for phi, we add this value to pi radians, to 180 degrees. So you add that angle to pi radians, you get 2.710216.427 radians. Get the tangent of this value, you will also get the answer negative 0.4602.4602877699. The same answer if you had used this value of the angle. If we use this value of phi of the angle to determine the amplitude, and note again, amplitude should always be positive. If we use this value to calculate the amplitude, we can use the position function to determine the amplitude. X is equal to a cosine omega t plus phi. If we set t is equal to 0, omega t will be equal to 0, and x will just be equal to negative 0.085 meters. Isolating A, we are able to calculate a positive value for the amplitude, 0.093572022255 meters. So we got a positive answer for the amplitude. That means this value of the angle is the more appropriate value for the phase constant. So phi is equal to 2.710 radians and A is equal to 0.094 meters. So again, when using sine function, cosine function, tangent function, please bear that in mind that certain values of the angle will give you the same answer for the cosine function, for example, or for the sine function, or for the tangent function, just as we have shown in this example. This value of the angle, get the tangent function. This value of the angle, get the tangent function, and you will get the same answer. Negative 0.4602877699. So please bear that in mind. And that's it for now. That's it for our discussion on the examples. part of our discussion on periodic motion. We'll continue our discussion on vibratory motion in the next video. In the next video, we'll take a look at the concept of pendulum motion. So, once again, that's it for now. Thank you for watching.